Yes, moving to next part of the presentation, it is for the design of the pressure vessel. Now, this is what the pressure vessel which we are going to design, and these are the design calculation and the basis for the design of the pressure vessel. So, it is being designed under the ASME Section 8 Division 1, and it is handling ethylene oxide, as you can see. Then there is it is horizontal limpet pressure vessel. The inner inside diameter is 1950, and the shell length, that is the cylindrical part of the pressure vessel, is 6000. It is having the ellipsoidal design 2:1. Then design pressure is almost you can see 7 kg per cm square, and on the limpet side it is 10 kg per cm square, right? So all parameters are converted. Temperature is 6 to 55 degrees centigrade for the particular fluid, right? Then there is a specific gravity is one, and it is almost having the kind of a water type of nature of the fluid. Percentage filling we are filling at 90%, and then the EO capacity is being given in terms of weight, and obviously it is being 100. Radiography is 100%. That is being shown. Joint efficiency one. So basically radiography will be 100%. Moving to next. It is like the another part, that is nothing but material which we are going to select. So you can see on both the sides the material is almost carbon steel. Sorry, material is stainless steel. So SA 240 grade 304L is stands for stainless steel, and all the material respect for the shell, design, stiffeners, nozzles, flanges, your reinforcement pads, lifting lugs, external and internal bolting gasket. And gasket, it is obviously SS304 spiral mount type of gasket. Saddle is there at the base of the pressure vessel, and foundation bolts are also of the same category. And it is a stainless steel material which is being used for the entire pressure vessel fabrication, right? It is because of the what type of nature fluid has it has been designed. Now, if you see by calculation for the volumetric calculation, the inside diameter and the shell length is being considered and some factors. So we'll get the capacity is approximately 19.86 the meter cube. So it is equivalent to 20 meters cube, or 20, you can say 20, one, sorry, it is almost in kg it is 20,000 liters capacity. Then calculation for the head, it is being done, and obviously based on that the head the design pressure comes out to be 7.20 kg per cm square, right? Moving next to the hydro test calculation. So almost always remember that test pressure is more than the design. So it is almost 1.3 times the design pressure, and considering the what are the allowable stresses for the ambient condition and design condition. So it comes out to be 9.36 kg per cm square. Moving next to the sorry, moving next to the just a second. Yes, moving next to the shell part of the design. So using all these parameters relevant to the pressure vessel, and for using the formula for thickness, T is equal to P into R upon S into E minus 0.6 times P. P stands for pressure, R is the internal radius, S is the maximum allowable stresses for the design temperature, E is the joint efficiency for the shell. It is equivalent to 1, and P is again pressure. So if you use the formula, we'll get the 6.001 mm is the thickness. But as we add some of the kind of allowances and all, it is equivalent to take. It is good practice to take 8 mm as the standard thickness for the shell. Shell is the cylindrical part of the pressure vessel. Moving to the dish end, again we use the same parameter, but the formula is different. So it is P into D into K upon 2 SC minus 0.2 times P. Here P into D is diameter, K is the again a factor which is equivalent to 1. And if you use this particular relation, we will get the thickness equal to 5.98, which is equivalent to 6. But if we add some uh, parameters, we are taking it on the more higher side, and we are taking it at equivalent to 10 mm for the safer side. And it will definitely going to increase the weight of the pressure vessel, but it will be useful in terms of modeling and another aspect. So these are the parameters for the shell, dish end, and the flanges. We have done the modeling of the same. Now expected outcome are nothing but we will design and analyze the pressure vessel for the operating condition using the ethylene oxide as the fluid, and it is nothing but it is a monolayer, that is single layer type of pressure vessel. So obviously all type of stresses, strain and deformation we are going to figure out on the pressure vessel side as well as limpet side. Then the system performance will be checked. If there are failures are going to occur, then we will be again changing some of the model or some of the design or some of the parameters relevant to the pressure vessel. These are my references for the pressure vessel, and thank you very much.